Saxon Advanced Mathematics, Lesson 3. Welcome, students. I just touched my book with a wet hand and made a big puddle, so we'll have to work around that. Today, we are starting the second week. Again, we're doing 2 homework lessons out of each lesson in the book. So evens or odds, odds or evens. We're still building up steam and getting these long review lessons behind us. There are some killer ones to come, but this one isn't too bad. Lesson 3 is not too monstrous. We're gonna work on some triangle geometry. And let's start with something that's probably quite familiar to you. If we have a right triangle, remember this only works for right triangles, and we name the legs A and B and the hypotenuse C, then we can say that A squared plus B squared equals C squared. Remember, A and B have to be the legs, the straight sides, and C is the hypotenuse. So it doesn't matter which one's A or B, we can switch those around, but C has to be the hypotenuse. And this will always be true. Okay, so big puffy cloud of knowledge around this whole thing. Add this to your formula pages, all right? Now, extending from this, we can develop what are called the Pythagorean inequalities. We covered these last year, so we're just going to summarize them. We know that if C squared equals A squared plus B squared, we just talked about that. That means that what we have is a right triangle. Right? And I'll draw a picture of a right triangle there just to remind you. If the square of the hypotenuse is greater than A squared plus B squared, that means we have an obtuse triangle. And remember, that's the kind that's like super tipped over, right? If C squared is greater than, pay no attention to that little squiggle. If C squared is less than A squared plus B squared, then we have an acute triangle. And that's the little guy like that, all right? So these are helpful because we can just examine the 3 sides of a triangle, and in this case, we let C equals the longest side. And we can test just by looking at the lengths of the sides, and we can find out what kind of a triangle we have. So, for example 3.1, it says the lengths of the sides of a triangle are 7, 5, and 4 respectively. Is the triangle a right triangle, an acute triangle, or an obtuse triangle? Okay, so it's saying take the sides, use this test, and tell us what you get. Now, C should equal the longest side, so we'll let that be C, and then these we know A and B can be either one, so we'll just call that A and that B. So we're comparing 7 squared, and we don't know if it's equal, greater than, or less than, so I'm putting a circle there to indicate that we don't know yet. 5 squared plus 4 squared, okay? So we're looking to see, is it equal, greater than, or less than? Let's do the calculation now. This is 49, this is 25, this is 16. Now we'll add them together, 49, and that's 41. So 49 is greater than 41. So that means it's this situation. So the triangle that gave us these is an obtuse. And that's correct. Make sense? All right. Now we're going to move on and talk about similar triangles. Similar is a tricky word because it has a normal everyday life meaning and a math meaning that is close, but it's more specific. A similar triangle means that it has the same angles but the sides are different lengths. It's what I call a click and drag triangle, because if you fooled around at all with shapes on any kind of it's like photos too, on any kind of a computer related thing, it's a click and drag situation, right? Because you're highlighting a shape and then you're pulling on the corner to expand it proportionally. That's exactly what similar triangles are. So, commit that to memory. Same angles, different length sides. That's what the word similar means. And so now we can do some fun examples with them. Oh, let me just show you an example of similar triangles. These guys can be similar. That angle's the same. Pretend I drew it perfectly, all right? This angle's the same. And this little toe angle is the same. Okay, that's fairly convincing. I mean, those are really crudely drawn, but you can see that click and drag, right? I made it bigger. This one, I scrunched it up to go that way. You can see how I could move back and forth between those two triangles just by expanding the lengths or contracting the lengths of the sides. All right, how can we use this in problems? I know, you're dying to find out. It comes in a problem like this. This is the classic bow tie pasta problem. You know those pasta shapes that are like bow ties? Maybe you don't. I don't know. This is what they always remind me of. We've got the lengths of the sides written in, but we've got a couple mysteries. Okay, so we're trying to find out these mystery sides. Find X and Y, that's our challenge. But John has also given us this information. This is probably all coming back to you now. What we see here is that these triangles must be the same because these two angles are the same and these two angles are the same. With triangles, if you've got two, you've got three, right? Because they have to add up to 180. So we know that these triangles are the same. And so we can redraw these so they look more like these, and then we'll be able to find out how to solve for the missing sides. So that's our first challenge, is to redraw this so it looks more like this. What I always do is I block off the second one and just redraw the first one exactly as it is so that my brain doesn't have to rethink that at all. Put the angles in exactly as they are, 4, 5, X. Now I draw a bigger version of the same triangle and I put in the angles the same because I know they have to line up. Now comes the tricky part. Now I have to refer back to this one and figure out which angles are which. And this is how I start. The side between the two marked angles is 7, right? There's the single, there's the double. There's the single, there's the double. This is the side between the two. The side that just comes off the 1 tick angle is the 6. So that's here. That's the 1 tick angle. And the side that comes off the 2 tick angle is the Y. So what I've done now is I've redrawn these triangles so that I can see the similarity between them. Now what I'm ready to do is set up proportions to solve for the missing sides. The first step in this is to find what we call the anchor proportion. The anchor proportion is the pair of sides for which we have a number in both the big triangle and the little triangle. So I look around, okay, this side has an X here, so I don't want to use this side. And this side has a Y there, so I don't want to use this side. This is where I can find my anchor proportion. Because on the corresponding parts of the triangle, corresponding sides, I have two numbers. So I'm going to make that 5/7. That is what I call my anchor proportion, and I use that to solve for the mysteries. Let's do the X first. X and 6 go together. So I can say that 5/7 equals X/6. That's how I use proportions to solve this. Now all I have to do is cross multiply and I'm good. And this becomes, I'm going to squish it over here. It's going to end up being 30 equals 7x, and then I divide both sides by 7, and I get x equals 30/7. I can't reduce it. That's my final answer. Okay, so super simple proportions. To solve for y, again, I use my anchor proportion, 5/7 equals, this time I want to solve for y, so I take the y and the 4. Notice that I always put the same triangle on top. I always put this number on the top, this number on the bottom. 5/7 equals 4/y. Cross multiply, I'm squishing now. 5y equals 28. I divide by 5, and I get y equals 28/5. Use your magnifying glass to read that. Okay? Using that anchor proportion is the key. Now, John sometimes uses this methodology to solve these. Sometimes he uses a scale factor. The scale factor creates needless confusion, in my opinion, and is not the way to go. I always solve similar triangles using this proportion method, and I recommend that you do too. If you look in the book, you'll see John's crazy drama. We don't want to go there. Okay, let's do another fun picture, shall we? Example 3.3. Another bow tie pasta. Looks like that. This time John gives us this. Okay, so how do we know for sure that these are similar triangles? Well, we know that one angle is the same, and we see these are vertical angles. So we know that those two are the same also. I added this tick mark this time. John did not tell us that, but we know that they're vertical angles. They have to be the same. So that is why this shape, this bow tie pasta shape, is so often used for these kind of problems, because we know that there's got to be a vertical angle there. So then they just have to tell us one other. All right, what have we got in terms of letters? X, Y, 7. One of the things I think about as I'm copying my vertical angles, or my similar triangles, is where am I going to find my anchor proportion? I can see right now that I've got variables here and here, so I'm pretty sure this 7 is going to be where my anchor proportion is. But I have to draw the triangles all the way in their fixed position. This one has 3 variables. That sounds challenging. So we'll do the same thing. Now we'll redraw this, letting the first triangle stay just the way that it did with my added tick mark, Y, X, and 7. And then we'll draw a bigger version of the same thing without really, I'm not really looking at this triangle, I'm just looking at this one and trying to kind of copy it. Okay, and then I carefully transfer the side information. Between the two marked angles is an 8. On the 90-degree side is a Z. And on just the tick mark side is the 10. All right, now I'm ready to find my anchor proportion and start solving. Here is my anchor. 7 over 10 equals, now when I look at the X, I see X matches with Z. That's gonna cause me a problem, isn't it? So I don't wanna do that first. What I wanna do is I wanna solve for Y first, because that looks nice and normal. So I'm gonna put Y over 8. So step 1 is to solve for Y. Okay, because I know I can do that using my old method. Okay, so then that becomes 8 times 7 is 56 equals 10y, right? Just cross multiply. Divide by 10. And I get y equals 56 over 10. I can cut those both in half and get 28 over 5. And I think John, yeah, I look at the answer and I see John has 5.6. And I go, oh, right, he converted this to a decimal. I prefer this answer, but John chooses this. So we'll go with him. I can see that it's right. Okay, so now I know that y equals 5.6. I still don't know what I'm going to do about this, because I can't find either one of those right now. But what I remind myself is we have other tools, and one of the other tools we have is Pythagorean. And I look and see, oh, on both of these triangles, I have 2 of the 3 sides, don't I? And it's a right triangle, so I know Pythagorean will work. So I'm gonna choose one of these sides, and I'm going to solve for the third side using Pythagorean. I can choose this side, or I can choose this triangle or this triangle, because I've got 2 sides for both of them. However, I would rather square these 2 numbers than square these 2 numbers, wouldn't you? I don't want to square 5.6. I can't do that in my head. So I'm going to solve for Z using Pythag. Orion. Does that make sense? So, this is the right angle, so this must be the hypotenuse. So I know that 10 squared equals 8 squared plus z squared. This is 100 equals 64 plus z squared. So I subtract 64 from both sides, and I get 36 equals z squared. Oh, how cute. Square root, I get z equals 6. It could be a -6, right? -6 is a root of this as well. But remember, in geometry, we can often discard negative roots because, or negative values, because the length of this is not -6. I'm sure of that. So I can be confident that this is the true answer. And I'm going to add it to my picture. Sometimes that helps. I did it there as well. I want to write y equals here too. Okay, and now we're ready to solve for x is our last one, and we can use proportion method because we've got this nice number here. So, and again, my anchor proportion is 7 over 10 equals x over 6. Oh, that's so cute and easy. And I get 42 equals 10x, and I divide by 10, and I get x equals, and this time I'm gonna go to the decimal because we did it, John did it last time, so I assume he's gonna do it this time. and I'm gonna write 4.2, and I'm right, John did do the decimals. Again, this could have been 21/5 and I would have been happier. But we can play the decimal game if that's what John wants to do. Usually mathematicians prefer fractions, but it's okay. Okay, we have two more similar problems to do. Similar triangle problems. Similar. Example 3.4. And this is introducing to us a classic presentation for similar triangles. Instead of the bow tie format, which is another classic presentation, this is the overlapping triangles. What we have here is two triangles. Imagine stickers, triangle stickers. And what we've done is we've taken a big triangle and a little triangle and we've lined them up here and then we've layered them on top of them. So what we're gonna do in just a minute is we're gonna peel the bottom one off. But first I wanna show you all the numbers and letters. A, B, C, go ahead and copy that. This is the information that John presents to us. What we have to do is we have to turn that into two similar triangles, which, like I said, mentally we're just gonna peel that up. We're gonna peel that first triangle sticker off. We're gonna redraw it here. This side is A, this side is 6, this length is 4. I'll put in these marks because they're important. Then I redraw a bigger triangle, and that's what this one is. So this goes here, right, because they have the same toe. This length I can identify as 10. This goes here. This length I can identify as C. And what's this side, how do I combine that? I just write A plus B. That seems weird, doesn't it? I look around at this and I go, oh look, here's a pretty anchor proportion. Honestly, I feel like this style of similar triangles, I like it better than the bow tie. Sometimes with the bow tie, I get kind of turned around as I'm flipping upside down. I'm sort of like Simone Biles getting the twisties. This is much easier for me to see how the triangles are similar. So there's my anchor proportion. So first, I think I'd like to solve for C because this A and B looks scary and I don't want to deal with it. So let's solve for C because that looks easy. We'll just use proportion method. My anchor proportion is 6/10. And then this is 4/C. Remember, I always put the triangle that's on the left, I put on the top. The triangle that's on the right, I put on the bottom. Okay, so then I get 6C equals 40. I divide by 6. And I get that C equals that reduced to 20/3. And John's gonna stick with fractions this time. He knows what's up. Okay, so now I've got C figured out. C equals 20/3. Okay, so now I look at my situation here and I go, well, I don't have either one of those sides. That's a problem. I need to find one of them. I can use Pythagorean for either triangle, right? Because I have 2 of the 3 sides on both triangles. I don't want to square that, so I'm going to stick with this one. So solve, for A using Pythagorean. So A is the hypotenuse in this case. So it's going to be 6 squared plus 4 squared equals A squared. Right? Those are my legs. That's my hypotenuse. Okay, 36 plus 16. And that is what? 52 equals a squared. And so then I take the square root and I get a equals square root of 52. Ew, that's ugly. 52. Let's see, can I break that down at all? That would be 2 times 26. And this breaks down into 2 times 13. So I can pull a pair of 2's out. So I can say a equals 2 times the square root of 13. Well, that's disgusting. It's correct, but it's disgusting, isn't it? Square root of 13. Now we have to use this proportion method to solve for that. Or, I mean, we could Pythagorean theorem, but I want to show you how to use this to deal with this. Because this a, now we can say, is 2 square root of 13, right? So this side is 2 square root of 13 plus b. So I'm going to set it up down here, even though it's super squishy. Now we want to solve for b. And the way that we'll do that is we'll use our anchor proportion again. 6 over 10 equals, and now we'll use these two sides, 2 square root of 13 over 2 square root of 13 plus b. Make sense? I put the value for a into both sides. And we can use it, even though it's got an addition in it, that is going to work. All right, I'm going to flip my page. I'm going to copy this over to the top of my next page. You can look out the window while I do that. It's getting ready to rain again here. So I'll copy this and then we'll solve it at the top of the next page. Okay. We're cross multiplying. I'm going to put parentheses around that because of that plus sign. I know I'm going to have to distribute to both parts, but I want to be careful about that. So 6 times this quantity equals those two times each other. I'll put this in parentheses too, just to show the multiplication. All right, now we'll distribute this. 12 square root of 13 plus 6b equals 20 square root of 13. All right, this is starting to look reasonable, right? I mean, it's not the most disgusting thing ever. Subtract the 12, square root of 13. 6b equals 8 square root of 13. Divide both sides by 6. And then this can reduce, right? We can take 2 out of both of those. So it becomes b equals 4 square root of 13 over 3. Oh my gosh. That's right, by the way. So we got all 3 answers. There's b, that's correct. C is 20 over 3, and A is 2 over 13. Now, I took these out of alphabetical order, and a lot of times I tell you to do them in alphabetical order, don't I? The moral of that story is do what makes sense to you. Do what seems logical. If you get stuck and you don't know how to move ahead, ooh, there's a clap of thunder. How exciting. If you move ahead, if you're stuck in the problem and you don't know how to move ahead, consider going alphabetical. But if you're cruising along, don't worry about it. Okay, last problem, and this is another classic way of showing similar triangles. This is example 3.6. Okay, so I told you that, I'm sorry, it's 3.5. I made that up. Bow ties are a classic way to show similar triangles. Overlapping triangles like this, the one we just did, are another way. And this one that I'm going to show you now is maybe the biggest granddaddy of them all. Looks like that. Okay, so there are the three different ones that we're exploring, but let me draw in more detail the one that we're doing right now. It looks like this. It has a right angle sign there. So we go, okay, well that's a right angle. But then it also comes down here and makes two more right triangles. So this one has a big triangle, a medium size, and a small, and they're all right triangles. How about that, sports fans? Okay. Then we're also told, as we always will be, that these two are equal as well. And we have so many letters. A, B, 4, 8, H, M, K. Okay. Again, our first step is to separate the triangles so that we can see them all individually. All right, and with these, what I did was I said, start over here and draw this one and then redraw the big one so it's oriented the same way. This one, it was easier. We could just peel the sticker off and draw the two. This one, I'm going to give you a different approach to the way I think you should solve it. First, draw the big one. Then draw a medium one. Then draw the little one. Okay, then we'll go back in and straighten them all out. The right angle has to go there on all of them. I know it doesn't really look like it. And this angle has to go down here on all of them because we want to draw them so they look the same, right? So on the big one, this side is B, this side is A, and this side is 4 plus 8. That's 12. Okay? Now we reorient ourselves and we're looking at the medium triangle. And what we see is the hypotenuse is, the hypotenuse is down here, is opposite the right angle. The hypotenuse is B. Wait. Yes, it's opposite the right angle, B. The side between the right angle and the double hash, that's an 8. And then this side over here is the H. It's tricky trying to ignore what you know about the old one and focus on the new one. And now looking at little baby boy, here the hypotenuse is A. Remember, the hypotenuse is always opposite the right angle marker. Between the two signs is the 4. And on the other side, just the right angle side, is the H. I feel like I've got this mixed around. Well, we'll figure it out as I go. So what we want to do is we want to solve for the letters. Let's just go alphabetically. Let's try to solve for A first. So what we want to do is look for the two triangles that have A's in them. And it's the big one and the little one. I think I've messed this up. 4 goes here and the H goes there. How do I know that that's true? I'll figure that out, but let's just go ahead. Okay, so we're solving for A. So A over 12 on this one equals 4 over A on that one. All right? I don't have an anchor proportion in this scenario, but I do have corresponding letters because I've repeated my different lines in the triangles. So now I can solve for this. A squared equals 48. I take the square root of both sides and I get A equals the square root of 48, and I can break this down, can't I? Let's call it 4 times 12, and this is 2 times 2, and this is 2 times 2 times 3. So look, I can take out 2 pairs of 2's, and so A equals 4 times the square root of 3. Beautiful. That's correct. Now let's try solving for B. And we'll do the same thing. We look for the 2 triangles that have B's in them, and that's these 2. So B over 12 equals 8 over B. I don't need an equal sign there. And now we get B squared equals 96. Take the square root of both sides. We get B equals the square root of 96. Again, we discard negative roots because this is geometry. 96, let's split that up. Well, we know that it's 8 times 12, so let's start with that. This is 2 times 2, and this is, oh no, there's 3 2's. This is 2 times 2 times 3. So again, we can take out a pair of 2's. But this time we've got that left and that left. So B equals 4 square root of 6. So far, so good. All right, and then for our final one, H. Which 2 triangles have H's? Okay, these 2, the medium and the small. So we say that H over 8 equals 4 over, no, I don't want to do it that way. I want to go no, that's what I like. H over 8 equals 4 over H. And now we get H squared equals 32. And we take the square root of both sides. H equals the square root of 32. And we break this down. It's 4 times 8. So it's 2 times 2. And then we grab 2 pairs of 2's, and we get H equals 4 square root of 2, which is also the right answer. Okay, so this is the third shape. And I feel like I confused myself up here when I was putting the letters on this triangle. Let me look at it again. This is the small triangle, it's here. This is the right angle that it goes to. This yeah, this is where this angle goes. I had it in the wrong place. That's what I did wrong. this flips up. This is the shorter side. This is the 4. A is the hypotenuse, opposite the right angle. And then H is the other leg. Okay, that's what I changed it to. When I first drew this triangle, I drew it wrong because I put this angle in the wrong place. But if you look at it, this is the short side, this is the long leg, short leg, long leg. The angle that we have marked is on the short leg. And there's the short leg. So I put that in the wrong place this time. All right. So moral of the story is these are tricky to sort out. You just have to go slow as you're pulling them apart and make sure that you're getting the angle information and the lengths of the sides set up properly so that you can solve. All right. Once I made that change, I was correct, but I just wanted to make sure I saw what I did wrong, and this was the mistake. No, this angle is not up here. It's down here, so that's where it corresponds in the picture. Okay, that's enough talking about that. That is the end of lesson 3. One of the nice things, well, I guess it's nice, I don't know, about this book is that there are no practice problems. I think I've talked about that already. So you don't have to worry about practice problems. Jump in, do the problem set, ignore the concept reviews. We're not doing those. And you're going to be really excited when we get to lesson 4, because I have a big surprise for you in lesson 4. Okay, that's the end of lesson 3. Thank you, goodbye.